Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one MCQ about mCPBA, meta-Chloroperoxybenzoic acid. The question is in front of you student. I request you, please read the question carefully, pause the video, try by yourself, and whatever answer you get, please write in the comment box, and along with that answer, please write few words explaining your logic. And don't worry, after some time we will get the complete description with mechanism. So now let's start. Now in this case student, please look at the problem little carefully. This is a very easy problem and one reagent is given, and see the reaction condition is room temperature RT. So from this thing you can clearly understand that it's a very selective reaction. Yes, obviously it is a selective reaction. So let's start the discussion. Now the mechanism, how the reaction is actually happening. This is actually an epoxidation reaction, because if you look at the structure of meta-Chloroperoxybenzoic acid, student, I repeat, benzoic acid here, and in this case the oxidation state of these two oxygen are -1, and they are actually called peroxyoxygen. They are actually responsible for the oxidizing property of this mCPBA, and what it oxidizes? It oxidizes the corresponding enol ether. So this part is the enol ether to corresponding epoxide at the first stage. So this is the oxidation reaction. So this is student, this is an epoxide 3-member ring. We know that epoxide are strained because they are 3-member rings. So what happened? That this epoxide got protonated in presence of acid. So this epoxide got protonated, and remember this oxygen is in heart center, so heart soft acid base interaction, so protonation happens on the oxygen. First point. Second point, so after protonation you can expect that this oxygen is carrying a formal positive charge, although oxygen is a electronegative atom and it is carrying a positive charge. It is not that much stable. Second thing, this epoxide ring is actually a 3-member ring. So 3-member ring is not that much stable because of ring strain. So due to these two factors, this ring undergo cleavage, and the cleavage happens from this side. This bond breaks, and ultimately it produces carbocation here, and another side is OH, because initially the oxygen was OH plus because of protonation. Now in the next stage what happens? This carbocation is in adjacent to another oxygen having this silicon oxygen bond. So what it can do? It can form a bond here. You may consider it's a resonance for octet filling at this carbocation center, which is actually a 6-electron species. So after this canonical form you can see here, so this is the canonical form, it is 8-electron structure. So octet fill structures, more stable structure. So this part I guess we have understood. Now another point you should know, that oxygen silicon bond is very strong, relatively very strong compared to a traditional you may consider single bond, sigma bond, or covalent bond. Why? Because the lone pair of oxygen which is in the p orbital can donate to the energetically accessible vacant d orbital of silicon. I repeat, energetically accessible vacant d orbital of silicon. So these lone pair of electron could be donated to silicon, and in this way the oxygen silicon single bond is relatively stronger due to partial double bond character. This thing we understood. Now look at here. Here the oxygen atom which was bonded to silicon is now having a positive charge. Positive charge simply signifies the deficiency of electron. So in this case what happened? This oxygen is electron deficient. Consequently you can say that this oxygen silicon bond becomes little bit weaker. Consequently what happened? The neighboring oxygen atom do a nucleophilic attack on this silicon center, and after this nucleophilic attack this bond come back on oxygen. Sorry, I should write it properly, on oxygen. Why? Because the leaving group is neutral. So in this way the carbonyl group is produced here, and another side is, you may consider, another silyl ether. Okay, so this is the overall product of this reaction. Now in the next stage what happened? That this silyl ether carbon silicon bond, this silyl ether hydrolysis happens in presence of acid, and what it does, it produces alpha hydroxy ketone. Why I am saying alpha? Because this is the carbonyl group and this is the alpha position of the carbonyl group. So this is alpha hydroxy ketone. Now by the way student, there may be a confusion, sir, what about this OEE? It is ethoxy ethyl protection of alcohol. Under this reaction condition it will not open. Now if I ask you that, student, can you make any guess what is the pH of this reaction medium? Obviously the pH of this reaction medium is slightly acidic. Why? Because mCPBA, after oxidation, it converts into meta-Chlorobenzoic acid, and by the way, meta-Chlorobenzoic acid is slightly more acidic compared to meta-Chloroperoxybenzoic acid or this peroxy compound. Actually the acidity of this OH bond is slightly higher compared to this OH, sorry, lesser. So this is low acidity compared to this carboxylic because of the stabilization of corresponding conjugate base like this benzoate anion. This number one. So here the H plus is used from where it came? It came from this meta-Chlorobenzoic acid, point number one. And another information, student, please remember that aqueous hydrolysis in presence of acid, fine. There is another option, that is fluoride mediated hydrolysis of silyl ether, which also produces the alpha hydroxy ketone, and in this way the driving force is stable silicon fluorine bond formation. This bond is also stable because of the same reason like this oxygen silicon bond. Okay, so what are the name reaction or key step associated with this process? Actually the overall reaction is named as rubotom oxidation, and the first step is epoxidation of alkene. I have already discussed, that is Friedrich reaction. Second thing, epoxide opening in presence of acid, I have already discussed the epoxide opening in presence of acid, base and neutral or slightly acidic or Lewis acidic medium. And third is the trimethylsilyl shifting from one oxygen to another. And final one, that is the silyl ether hydrolysis in presence of acid. So what is the answer? Answer is option A. Okay, now question, student, you may think that, sir, option A is correct, fine, but why not the other? It is actually a di in this molecule. Why not the other double bond, means other side oxidation didn't happen? Because of, student, a very unique canonical form, means this is the lone pair of oxygen. So these lone pair will be pushed here and it will open. So you can say that this carbon center is more nucleophilic, and this conjugation is not available with the other double bond. Okay, so that's why reaction happens on that double bond, because of electron richness. And these epoxidation is, student, actually electrophilic epoxidation, means the double bond act as nucleophile and mCPBA here act as the electrophile. Okay, so reaction happens, the alpha to that carbonyl. So this is rubotom oxidation. I have already discussed a dedicated video, you may visit. So this is the product. Now if you look at the other option, this is a simple ketone, alpha hydroxy ketone will be produced, so it is not. Second thing, the hydroxylation on the other double bond, not possible. And another thing here, means epoxidation happens on these double bond, this is actually an isolated double bond. So this, no, not possible. Why? Because as I told that these mCPBA mediated epoxidations are electrophilic epoxidation reaction, and the epoxidation will happen on the maximum electron rich double bond present in the molecule. So here epoxidation not possible under this reaction condition. Okay, when these OTMS double bond, means silyl enol ether part is intact, then reaction cannot happen here. First reaction may happen here, later on possible, but this is not, this option not possible because the OTMS attached double bond is intact. So in conclusion, what you have learned, the rubotom oxidation is high yielding chemical reaction between silyl enol ether and peroxy acid to corresponding alpha hydroxy carbonyl derivative. Silyl enol ethers are similar to electron rich alkene and active for electrophilic reaction. This is because the canonical form. So this is, it comes, it opens, so it produces this canonical form. Because from this canonical form you can say that the carbon atom is electron rich, nucleophilic, so that's why it participates more efficiently under epoxidation condition in presence of mCPBA, which is an electrophilic reagent. Enolates are mild nucleophilic because of this canonical form, and such epoxidation known as electrophilic epoxidation I told. And finally, the sterile ether hydrolysis could efficiently be done in presence of acid, alkali or fluoride ion. So this is the end of this discussion. I believe this video may be useful. If it is, please help this channel grow, and if possible, please visit my another channel where I upload global warming and climate change related videos. So stay happy, stay blessed. See you in my next video.